Okay, let's talk a little bit more about thermodynamics. We've touched on Q, talked about delta H, and now we have a few more terms to go through. So, thermodynamics is a study of relationships between physical energy and work associated with a chemical or physical process. And we use these concepts to determine whether something's going to get hotter or colder, whether a particular reaction will take place spontaneously or not spontaneously. So we have a few definitions to go through. So, chemical or physical processes have a natural tendency to occur in one direction under certain conditions. If the reaction is written in such ways that the forward reaction takes place without any need for intervention or any kind of input from outside, then it is considered to be a spontaneous process. A non-spontaneous process, however, is something that requires continual input of energy from an external source to occur. So an example of this, a spontaneous reaction, is the battery in your cell phone. It will continue to put out energy as long as it has energy and power your phone. And as soon as your phone is dead, now we have to plug it into the wall to recharge it. Recharging that cell phone is a non-spontaneous process because we are putting in energy. So they can be spontaneous at one temperature but not spontaneous at another temperature. This explains why if your battery gets very cold in your computer, it will die very quickly. And the same thing happens with car batteries. You'll see a lot of people getting new batteries when it first gets very cold or first gets very hot, because temperature does have an effect on those reactions. So it is not correlated to the speed of a process. We will be studying in the near future kinetics, and this has nothing to do with whether something is fast or slow. It just happens whether it will happen at all without input from outside. Radioactive decay is a spontaneous process, but some of those take millions of years to go forward in terms of any kind of appreciable amount. So it has nothing to do with time or how fast. It just tells whether or not it will favor the products. Entropy is another state function. Entropy is denoted with the letter S. We didn't have any other letters that were related, so we use entropy. And entropy talks about the order or disorder of a system. If a system is random and very disordered, then it has high entropy. If something is very ordered and neat and evenly distributed, then it has low entropy. So, when we're looking at a system, if it is going from a solid to a liquid, that increases the disorder, so delta S would increase. So when entropy of a system decreases, delta S is less than 0. And when delta S is greater than 0, it's positive, which means as entropy increases, the disorder of a system increases, or it's positive. So the disorder for one substance as it goes from a solid to a liquid to a gas is increasing. Gases are always more disordered than their liquids, and liquids are always more disordered or higher in entropy than their solids. It is difficult to compare across substances. However, any reaction that has more gas moles as a product will have an increase in entropy. So entropy is typically greater for heavier atoms and more complex molecules because they have a lot of different ways they can rotate, or they can be twisted and turned and pulled and pushed. It increases when a system is heated because now they have more energy to achieve more random positions. And so you should be able to tell me whether a system is increasing or decreasing in order if you look at the state of matter and the temperature. So The second law of thermodynamics implies a relationship between entropy of a system and spontaneity. And it says all spontaneous changes cause an increase in the entropy of the universe, where the universe refers to the system and the surroundings. Remember, we look at the system, which would be the beaker I'm doing my reaction in, and the surroundings is everything outside of that beaker that I'm doing my reaction in. So a change in the entropy of a system and its surroundings, or the entropy of the universe, is denoted as delta S UNIV. The second law of thermodynamics can be more compactly expressed as the entropy of the universe is always increasing. If the entropy of the universe were less than zero or decreases, then the process is non-spontaneous. If the entropy of the universe is equal to zero, then the system is at equilibrium. So let's think about the third law of thermodynamics. Consider the entropy of a perfect, pure crystalline solid with no associated kinetic energy of its particles. That is, that the crystal is at a temperature of absolute zero, with the only possible microscape, the microstate, the entropy is at its lowest state. The limiting condition for a system's entropy represents the third law of thermodynamics, and that is that the entropy of a pure, perfect crystalline solid is at 0 Celsius is 0. So we can compute standard entropy changes for any process. And guess what? We look them up in a table. So last letter you need to know is G, which is Gibbs free energy. It is a state function. That means that it is independent of the path taken to get to a particular state. Just the starting and the ending states are needed to be known. And it can be used to predict the spontaneity or whether a reaction will occur without input from outside. A negative value for delta G indicates that it is a spontaneous or a reaction that will occur without input. If it is positive, it indicates a non-spontaneous process, which means that the reaction will not occur unless energy is put into the system. And if delta G is 0, the system is at equilibrium. We will be doing a unit on equilibrium in the near future, so you'll get to have lots of fun with those calculations. The number of approaches to a computation of free energy are possible. So I think that about covers it. We're going to calculate now delta G, delta S. You've already done delta H, so you should be all set. Thanks. I'll see you in class.